Thank you, Professor, for the introduction. Thank you, guys, for coming today. I will present you most of the work that has been done during the last 3 years of my PhD studies under supervision of Antonio Loria and Elena Pontley. And the work that has been done was related to stability and stabilization of network systems. So to put this presentation in general context, let me try by introducing a finite set of dynamical systems where xi is the state variable of the each system, fi is the dynamics, and ui is the control input of the each system. So we say that our network, as represented in the picture, is decentralized, means that the each system in his control law uses the information, his own information, and the information that comes from a certain number of neighbors that belongs to the set Ni. So the set Ni determines the set of neighboring agents for the system I. So regarding this architecture of the network, a lot of situations can be present. So for example, we can consider the case where the agent dynamics are identical, in which case we have homogeneous network, or they are different, in which case we'll have what we call heterogeneous network. And also, the dynamics can be linear or nonlinear. And also, we can consider a lot of situations regarding the graph topology. So the graph topology can be unidirectional, means that if two agents communicate, the flow of information goes in only one sense, or in a bidirectional case, if they communicate, the information goes in both senses. And also, we can have constant graphs, which means that if two agents communicate, they will still communicating all time. And also, we can have consider time-varying graphs, which means that some two agents are neighbors now, but after a certain time, they will not be neighbors anymore. Also, we can consider different types of interconnections. For example, static interconnections or invariant interconnections, time-varying interconnections. We mean by time-varying interconnections that two systems communicate, but not all time, just at certain interval of times. And also, the transfer of information from one system to another can be affected by delay. And also, we can consider the case of strong interconnections. I will define this notion of strong interconnections in the last part of the presentation. So under some of those situations, we propose to study 3 problems. The first problem is the consensus problem. In consensus problem, the goal is to steer all the trajectories of the systems in the network toward the common point, which is called xc, the consensus point, up to a certain gap vector. And this gap vector is a constant vector which determines the formation pattern around this consensus point in steady state. Another problem is the leader-follower problem. So it's similar problem, but in this case, we add the fact that the consensus point is not any point, but is a point that corresponds to a trajectory of certain leader. So what we want is to follow this leader up to a certain gap vector delta for each agent in order to have certain geometric structure around this leader and following it with respect to time. The third problem that we will study is synchronization problem. Here we give a very general definition about what we mean by synchronization. Synchronization concerns common behavior in steady state. So for example, if you have oscillators, each oscillator has its natural frequency. After interconnecting them as we define in a network, if we can show that all the systems will have the same frequency after interconnection, so we say that we guaranteed synchronization in frequency. So our approach, since in the title it was mentioned that we do stability and stabilization of network systems, so our approach consists on transforming the previously cited problem into stabilization problems of classes of linear or nonlinear time-varying systems. And how we do this? We try to find each time error coordinate E, which is function of the original coordinate, such that the previously cited problems are solved if and only if the error coordinate is equal to 0. And then what we do is that we derive graph conditions and control laws in order to guarantee some stability properties of the error coordinate. Our approach is based on the use of differentiable Lyapunov tools that I think you know. So Lyapunov second methods and its derived method. So the rest of the presentation is follow this outline. So in the next part, I will consider a network of linear time varying systems that are interconnected with the graph that is time varying. And then I will consider a more complex network in terms of agent dynamics. I will consider a network of nonholonomic mobile robots that are nonlinear systems that are interconnected with static graph, which means that the interconnections in this case will be constant. And in the last part, we will consider also a more complex case of networks, which is network of heterogeneous oscillators. And we will try to study synchronization of those oscillators using strong coupling between them. So and I will end with the conclusion and some open problems that we didn't solve during the last week. So let me start with the first part. Assume that each agent in the network is modeled by this linear time varying system, where UI is the control input. So now I will stress in this control law. This control law is widely used in multi-agent systems, and it has the simple meaning and the intuitive meaning that the control UI try to steer or to push the agent toward the barycenter of neighbors. So this is expected to guarantee consensus, because if we have a lot of agents and each one will move toward the neighbors, then maybe in steady state they will end in the same point. So the interconnection here, LIGT, is time varying because we consider time varying graph. So LIG can be equal to 0, in which case XG with XI does not communicate. And if it is different from 0, so we say that there is communication between the two agents, I and J. So in compact form, we have this final closed loop system. So the part in blue is just the compact form of the control law, and it involves the matrix L, which is called Laplacian matrix of time varying graph. So the goal is to analyze uniform consensus of this closed loop system. So we know that from the definition of consensus, that uniform consensus, is equivalent to uniform asymptotic stability of the set where all the states are equal. We add uniformity since we have linear time varying systems, and having uniformity in our stability conclusions is important to guarantee robustness to small perturbations and some other benefits. So the question now is, what are conditions on our graph or on the Laplacian matrix L of t in order to guarantee uniform consensus? And since we have uniform asymptotic stability, this means that we have uniform exponential stability. So how can we, in this case, estimate the convergence rate? So this, no, it's something depends on the initial conditions. In this case, it's not given because we don't have leader. When we have leader, so XC will be given. So this problem has been widely studied in the literature. For example, if we take a simple case of network of integrators, we end up with, in closed loop, with linear time varying system, x dot equal minus L of tx. So this system for general case of time varying graphs have been widely studied in the literature, starting from the work of Luc Moreau, his very famous work, when he shows that if we have connectivity of the uniform graph, which is defined by this formula, plus some extra conditions, he can show that uniform consensus is guaranteed. And this kind of assumption is similar in the earlier works due to Wei Ren and Jedbabey and co-authors. But in those two references, they study just piecewise constant graph. How the graph switches between constant graph with certain predefined interval of time. And also the work of Shi and Johansson, where they try to explicitly estimate the rate of convergence under similar assumptions. In some other literature, they tried to show or to guarantee just consensus without uniformity, so you have just to prove convergence. So in this case, the main assumption is related to the connectivity of the unbounded graph. What we mean by the unbounded graph is that the big T in the uniform graph, you replace it by infinity. So you get unbounded graph, and if this unbounded graph is connected, then you have to add some assumptions to guarantee consensus. And also, for general case of linear time invariant systems, the work of Skarduvi and Sipulk and the work of Wayland and co-authors use the graph assumption from Morrow to deduce output feedback control, which is not the case in our study since we use static feedback, but they use dynamic output feedback to prove the result. So a common thing between all this literature is that when they deal with time-varying graphs, they always use trajectory-based approach. And they use mainly a min-max non-differentiable Lyapunov function. So it's trajectory-based approach. They prove consensus by taking part of trajectories, and they prove that the set, the convex hull of all the agent is shrinking after a certain period of time, which depends on the connectivity of the graph and so on. So in our case, we will try to propose some differentiable tools, which will make the problem simpler since we have the Lyapunov function. You take the time derivative, you will see that there is that the time derivative is negative definite, and it's very easy to prove the result. So we will try to propose those kind of differentiable Lyapunov tools to solve those kind of problems under time-varying graphs. So before that, I will define some notions. Let me consider bidirectional graph as shown in this picture. And let me denote by R the number of all the links in this graph. So in this graph, we have 7 links. So all possible links that may occur in time are considered. So we have 7. And we gather the weights of those links in diagonal matrix W. And then I decompose this matrix, this diagonal matrix, into 2 parts. The first part is W tau, which contains the links of spanning tree. So the links that are in blue in the pictures, omega 1 up to omega 5, are links forming spanning tree. What we mean by spanning tree is a tree which contains all the agents. So it's spanning tree. That's why we use this terminology. And omega C will be the remaining links that we call cycles. So we will make this important assumption on the links forming spanning tree. We will assume that that W tau is persistently exciting. Let's see the definition of persistence excitation. For symmetric semi-positive matrix A of t, we say that it is persistently exciting if this integral holds for a given tau and for a given mu greater than 0, which means that A of t has not to be positive definite all time, but only at some intervals of time. So now if we come back to our spanning tree, so the communication that happen in spanning tree has not to be positive, has not to be greater than 0 all time, but just at certain intervals of time. So in a joint work with Shrikant Sukumar and his PhD student from Mumbai University of India, we tried to study the particular case of network of simple integrators. So the closed loop system will have this simple form. And we showed us that following our approach, the first part, we need to find error coordinates to transform consensus into stability, and then show uniform exponential stability in those coordinates. So we prove the existence, and we compute explicitly those matrices, H and gamma and lambda, such that if we consider the error coordinates E equal h multiplied by x, in the new error coordinates, we end up with this system that is called gradient system. Gradient systems have been widely studied in adaptive control literature, and there is a well-known result which says that we have uniform exponential stability in the error coordinates for this system 1, if and only if the matrix is persistently exciting. So what we show in our result is that if our spanning tree is persistently exciting, then this matrix is also persistently exciting. So our problem is solved under the assumption that we made on the graph. Also, in this paper, we provide for the first time an original strict Lyapunov function for gradient systems, which allows to estimate the convergence rate. After that, similar approach was followed by Anderson. Since Brian Anderson has been working a lot on this gradient system and adaptive control, and he developed the notion of uniform observability. So he used all those tools to solve this problem in similar way. So now, if we try to consider the case of more complex networks, I was interested by this case of harmonic time-varying oscillators. So the matrix A of t is given by this form, skew-symmetric matrix, 2 by 2. And omega is the speed of oscillation, is the frequency, which is time-varying. Now, if we use our control law, our static protocol of communication, we end up with closed-loop system, which is in the right. So it's a very simple system. L of t is positive semi-definite, time-varying. Omega as well is time-varying. The system has particular structure which we can find in model reference adaptive control systems. But in model reference adaptive control system, the matrix L of t is replaced by something Hurwitz. In our case, we don't have this. So this is more relaxed class of system. So we proposed this problem to a master student that graduated last year. And working on this problem, we showed that we can also propose error coordinates following the same steps in the previous slide. And we can show that we guarantee uniform consensus if and only if the system in the error coordinates, which is given by this form, is uniformly exponentially stable, where d of t is semi-positive, symmetric semi-positive matrix. So this is very simple system. They have skew-symmetric form. Trajectories are bounded. But the thing is that d of t is not positive definite. It's just semi-positive definite. So it's harder. So you can't use LaSalle and adaptive control, Barbala and adaptive control tools for this case. We showed this surprising result, which says that if our spanning tree is persistently exciting, this will imply naturally that the matrix d of t is persistently exciting, but this is not enough to guarantee uniform exponential stability of this system, even if you take omega equal to 1. So you just put here omega equal to 1, constant. This matrix, persistently exciting, this is not enough to guarantee uniform exponential stability. So we had to deal with this problem and to formulate the adequate sufficient conditions to guarantee uniform exponential stability of this system. And we end up with this condition, which we called dwell time on the excitation interval. Why we choose this condition? Because the counterexample that we had, so we proposed the counterexample for this system. We take d of t as persistently exciting matrix, but it switches fast. And the frequency of switch gets faster and faster with time. And with this, we use the uniformity in the convergence. So to avoid this situation, we assumed dwell time on the excitation of our links forming spanning tree. Plus to that, we add the condition of persistence of excitation of the product between this frequency, natural frequency of the oscillators, and the product with the the intensity or the weights of the spanning. And with this condition, we are able to show uniform exponential stability and to provide strict Lyapunov function for this system. So finding necessary and sufficient conditions for uniform exponential stability of this system, I think is open problem, and yeah, it's open and not that easy, even if the system looks simple. So now we propose to consider more general case of networks in terms of agent dynamics. We consider a network of non-holonomic mobile robots, and we will try to study the leader-follower formation control problem, and then the leaderless formation control problem as well, but in the presence of delay in the transfer of information between the systems. So let us consider network of non-holonomic mobile robots. So the one here in the top is a leader. So for the leader, we consider this kinematic model. I think you are guys familiar with this. So V is the translational velocity, omega is the rotational velocity, and theta 0 is the angle, x, y are the positions. And for the followers, we consider complete dynamical system, the complete dynamical model. So we have the kinematic level and the dynamics level. So here the control are the torques input, and this is the model of our network. So now our approach is very classical and standard as an approach. We propose first to solve the problem at the kinematic level. So at the kinematic level means that our virtual controls will be the velocities, Vi and omega I. So we will design Vi and omega I as our virtual control inputs, which are not in reality, such that our formation problem is solved. And then we go to the dynamic level. We design the torque inputs, the actual control input, in order to guarantee the tracking of the virtual velocities with finite L2 norm. We do those two steps separately, and then we have to make sure that if we put everything together, our conclusions remains valid. So we will be able to still be able to solve our consensus problem if we put everything together. So our contribution is that we consider in this case very different behaviors of the leader's velocities, because the control design and the stability analysis depends on the leader's behavior. And also we assume that our communication graph is particular topology, which is fixed, and particular, which is spanning tree topology, and which is the minimal topology required to solve consensus problems in general. So now we transform our problem, we reformulate our problem at the kinematic level. So for the leader, we keep the same model. And for the followers, we decompose the velocity into two parts. The first part, which is in blue, are the virtual controllers. So we will design some formulas for those variables. And the other part, which is in red, are the errors, because we cannot inject to the system the virtual velocity. So we will transform our problem into a problem of robustness with respect to the variables in red. So the variables in red will be considered as perturbation, as vanishing perturbation. So we propose to solve this problem under three situations. The first situation is called the tracking scenario. In the tracking scenario, we assume that the sum of square of the leader's velocities are persistently exciting, which means that the leader is just moving, not stopping. The second case is what we call robust agreement scenario, when the limit of the leader's velocities with time is 0. So the two scenarios are complementary. If you are not persistently exciting, then you will converge to the origin, and vice versa. And in the third part, we propose unified control law that solve the two problems simultaneously. So we propose one control law that even if you are in the first scenario, either if you are in the first scenario or in the second one, you still solve your leader-follower formation problem. So for the mobile robot, this kind of problems has been widely studied in the literature for one follower case or for multi-agent case. But we believe that no much attention has been taken to the leader's behavior. For example, in some works, they assume that just the translational velocity is strictly positive. In some other works, that they assume that only the rotational velocity is persistently exciting. So there is no, we didn't find work that cover all possible behaviors of the leader's velocity. And also for the problem of simultaneous tracking and agreement, which means one controller that solve the two problems, there is just few literature even for one follower case. And the only work which exists for multi-agent case is the one due to Wang and two others. And in this case, even if they consider general graph, they assume that the desired velocities are commonly shared to the network. And also, what they can prove is only practical convergence of the error coordinates. So the convergence is just, they converge only to a small neighborhood of the origin. For our case, we consider more general behaviors of the leader's velocities, even if our graph topology is simple, it's just spanning tree topology. And we establish some original ISS type robustness properties of the kinematic closed loop system. So since we have spanning tree topology, we follow our approach. We try to find the error coordinates. So we take the error between the system and his father, because if we are in spanning tree topology, each system has only one father. So he receives the information from only one other system. So we consider this error, and then we write this error in the frame of the father, and we end up with this system in the error coordinate. So what we want to do is to design VI star, omega I star, in order to guarantee convergence of the error coordinates when the perturbation parameters in red are converging with finite L2 norm. So it's just a robustness problem. So the first case, if we consider the tracking scenario, we have this result. We propose this control law, under which we show that our closed loop system is uniformly semi-globally exponentially stable. It means that you are exponentially stable, but if you start from compact, when you don't have perturbation. So if you don't have perturbation, then you have this stability property. And if you add the perturbation, we show that we are integral ISS with respect to this perturbation. So since we are integral ISS, if we have finite L2 norm plus convergence, this means that the errors will converge as well. So we solve the problem in this case. So we have to remark that similar controller was proposed in the very early work of Kanodas and two others, but in their work, they just prove global attractivity. And they consider only the kinematic level and only one follower. So here we have developed more tools to allow more strong conclusions. Also, if we consider the agreement case where the leader's velocities converge to the origin, we propose this, what is called the delta persistently exciting controllers that has been developed by my advisor. So under this control law, we show that the closed loop system is strong integral input to state stable with respect to both the leader's velocities that are converging and the perturbations. As a conclusion to that, if this vector converges to the origin, then the errors will converge to the origin. It's a straightforward conclusion, consequence from the strong integral ISS property. Strong integral ISS property means integral ISS plus small ISS. We have to guarantee two properties. So as I said, the robustness analysis here in this case, we believe that it's original. Now, we propose a unified controller that solves both problems. So what we did is very intuitive idea. is to combine the previous controllers using a weight function lambda. And this weight function has a certain property. It's like smooth supervisor, which means that if we are in the first scenario, tracking scenario, lambda will be vanishing signal. So we promote the tracking controller. And if we are in the agreement scenario, lambda will be greater than 0, and the leader's velocity will converge to 0. So in this case, naturally, we promote the stabilization controller. So with this, we show that our closed loop system converge to the origin when the perturbations converge and are finite L2 norm. And also we show this strong result that if we don't have perturbations, we guarantee uniform global asymptotic stability of the error coordinates. So we have, in this case, more relaxed assumptions on the leader's velocities, and we were able to consider multi-agent case. Second part, we have a leaderless formation control problem. So we don't have leader, we want just to solve consensus problem. So we have multiple systems of this form that model the dynamical model of mobile robots, and we want them to converge to the same point. So we propose this simple change of coordinate just to have in steady state certain geometric structure around the consensus point. So delta I are constant. And we end up with this system in a compact form. So we have this system, which is double integrator-like system. It's not double integrator, but it has similar form. And we want to solve consensus problem. So first, we solve this problem. We solve what we call partial consensus problem. We mean by that consensus in positions with given orientation. So each system knows its desired orientation, and we need just consensus in positions. And then we studied what we call full consensus problem, which we mean by that consensus in both positions and orientation. And for this, following our approach, we need to define the error coordinates. And since in this case we have a general bidirectional graph, we define what we call the distributed error coordinates, which are the error between the system and the barycenter of the neighbors. And in compact form, these error coordinates involve the Laplacian matrix, since we consider the barycenter of the neighbors. So it involves naturally the Laplacian matrix of the graph. And we show that we solve our consensus problem if and only if we guarantee asymptotic stability of those distributed error coordinates. So this is the first step. So before going further with the result, we know so far that from the famous Brocket result that nonholonomic system cannot be stabilized by smooth feedback law. So you have to use either discontinuous feedback law or time varying feedback law. So in the literature you can find method with both type of controllers. But our contribution regarding the existing work is that we propose smooth time varying controllers for which we prove uniform global asymptotic stability of the error coordinate, of course, and we propose for the first time strict differentiable Lyapunov functions that allows us to extend our result to the delayed case, as we will see. And we will extend our strict Lyapunov functions to strict Lyapunov-Garazovsky functionals. So our controller, for the translational part, we consider simple PD-like controller. And in the error, we put the distributed errors. And for the rotational part, we use as well a PD controller plus a certain term that we will discuss the importance when we see the structure of the closed loop system. And also, for the full consensus problem, we use a PID controller in the rotational control load. Since we need also consensus in the orientation, so we need to involve the Laplacian matrix in the control law for the rotational velocities. That's why we have this PID structure, where the functions, the time-varying functions P and Q are related with those differential equations, just to guarantee the excitation of some parts of the system that we will see after. So the closed-loop system for both problems will have this form. So as we can see here in the translational part, the three equation in the top, that we have negative term in V, and we have here omega bar that appears in skew symmetric form. So the role of the term P of t here is to excite the rotational velocity until we have convergence of E and S. And once E and S converge to the origin, this term will not exist, and we end up here with stable, linear stable system. So this is the idea of this control loop. And similar idea is in the full consensus problem. So as I said, we show uniform global asymptotic stability of this nonlinear time-varying system by means of strict Lyapunov function. Strict Lyapunov function means that Lyapunov function, when you derive, you get something negative definite, not semi-negative definite, strictly negative definite. So after that, we propose to extend this result to delayed case. So in the delayed case, the change occurs in the distributed errors. Why? Because we are not able to compute the error between system and the average of the neighbors at time t, since we receive the information from the neighbors with certain delay. So we will have what we call the delayed error coordinates, which have similar form. And in our control law, we use the certainty equivalence principle. So we keep the same controllers, but instead of putting the error coordinates, we put the delayed version of this error coordinate. And the same thing for the rotational part. And we show that for given upper bound on the time delay, so the time delay is time varying. We have time varying delay, but bounded. So for a given upper bound on the delays, and for a given upper bound on the interconnections, we are able to tune the PID and the PD parameters in order to guarantee uniform global asymptotic stability of the closed loop system in both situations. And also, we propose strict Lyapunov function to do that. Now, the last part of the presentation, so far we considered only the case of homogeneous networks. So all the systems have the same model. In this case, we will consider a case of heterogeneous network. So the system have different models, and they are oscillators. And we will consider the case of Andronov-Hopf oscillators. So as shown in this phase portrait, Andronov-Hopf oscillator is a system which has the origin as an equilibrium, which is completely repulsive, and which has periodic orbit. So all the trajectories that avoid starting from the origin will converge to the periodic orbit. So we say that the periodic orbit is almost globally asymptotically stable, since we have to avoid starting from a point which is of null measure set. So before going further in the result in this case, let me start with small comparison between two consensus problems. So the first is the classical consensus problem. So we have a network of nonlinear systems interconnected with static protocol of communication, which involves the Laplacian matrix L. But in this case, we have strong interconnection, which is determined by the parameter sigma. So sigma is the degree of freedom, so we can make sigma as large as we want in order to guarantee our result. So now, in the first part, in the classical consensus problem, if we assume that we don't have nonlinearities, we have just simple integrators, so we can always find transformation that decompose our state variable into two parts. The first part, xm, is the average of all the agents. We take all the states and compute the average. And the other part is the error between each system and the average. So if we compute the dynamics in this error coordinates, in this new coordinates, we end up that the average has null dynamics if our graph is bidirectional. And the error coordinates has this exponentially stable dynamics here. So from here, we can see that the errors will converge to 0, and all the agents will converge to the average. So in steady state, everything will go to the average of the initial condition. Now, if we consider nonlinearities in the system, so the closed loop system will have this form. And if we adopt the same transformation, the average and the error between system and the average, we end up with those two dynamics that are interconnected. So the first one is the emergent dynamics, is the dynamics of the average. And we will see why we call it emergent dynamics. And the other part is the synchronization errors dynamics. What we can see here is that if we put sigma equal to infinity, which is not possible, but let's say we have sigma equal to infinity. So here we will have the errors that will converge to the origin instantaneously. What happens in this case is that this interconnection term will be equal to 0. And all the network will have the same behavior, which is the behavior of the emergent dynamic. And this emergent dynamics depends only on the nonlinearities that are present in the network. Now the question that we want to ask, since we are not able to set sigma equal to infinity, what happens if sigma is not equal to infinity, but it is chosen sufficiently large? Can we guarantee continuation of this behavior from sigma equal to infinity to sigma sufficiently large? This question we will try to answer using singular perturbation theory. So when the nonlinearities are all the same, and if we have a homogeneous network, it is easy to expect complete synchronization when sigma is sufficiently large and the nonlinearities are sufficiently regular. But in the case where they are different, all the existing works, all what they show is practical convergence to the emergent behavior. So we have here the emergent behavior, which appears when sigma equal to infinity. When sigma is sufficiently large, we have just practical convergence to this behavior. So we will be in the neighborhood of this behavior. So in our case, we will try to look to this particular form of network as a system evolving in 2-time scales, and then we will use stability and to do stability analysis, singular perturbation theory that was developed by dynamical system literature due to Anosov and Knishan. So we will apply our result for the case of Andronov-Hopf oscillator. So if we consider a controlled Andronov-Hopf oscillator, its dynamical equation in the complex plane is given by this, where ui is the control. So we take u as our static protocol of communication with parameter sigma that characterizes the strength of the interconnection, and we end up with this closed loop system. So we have bidirectional Laplacian graph, which is symmetric, and we know that we can always find an orthogonal decomposition of this matrix such that we isolate the null eigenvalue, and we have the all other eigenvalues that are different from 0, and that they are real, of course, because it's a symmetric matrix. So after applying our transformation, the average and the error between system and the average, we end up with this system in the new coordinates. Now, if we define epsilon to be equal to 1 over sigma, we end up with this system in singular perturbation form. So if epsilon equal to 0, means that sigma equal to infinity, and so on. So what we know that if epsilon is equal to 0, we have an emergent behavior, and we would like to know what happens if epsilon is not equal to 0, but is chosen sufficiently small. So for this particular case of Andronov-Hopf oscillators, we know that if epsilon is equal to 0, what we call the imperturbed system, we know that this system admits an almost globally asymptotically stable periodic orbit. So you interconnect Andronov-Hopf oscillators, you set the interconnection parameter to infinity, you end up in the emergent dynamics with something that has an almost globally asymptotically stable periodic orbit. So, since we have periodic orbit, the existing literature on singular perturbation theory is not applicable because it was applied mainly for the case where the origin is in equilibrium for both the perturbed and the unperturbed system. So we needed other tools for that. And we show this main result, which states that it is always possible under some regularity for this particular case of Andronov-Hopf oscillator to find upper bound on epsilon, such that for each epsilon small than epsilon start, the perturbed system will admit non-trivial periodic orbit, which is sufficiently close to the emergent dynamics, which is also periodic orbit, and which is also, in this case, almost globally asymptotically stable. So we say that we have a continuation of the behavior from the case where we don't have perturbation to the case where we have sufficiently small perturbation. And then this result has been extended to general case of nonlinear systems admitting periodic orbit, and we will try to submit this paper soon. So as conclusion, we provide some differentiable Lyapunov methods to study consensus problems, formation problems for mobile robots, and some synchronization problems, and some open problems that I was not able and we were not able to solve yet is to consider the differentiable Lyapunov tools for the case of directed graphs that are time varying. Because as I said, all the existing literature which dealt with time varying graphs, the approach is based on min-max non-differentiable Lyapunov function and on trajectory-based approaches. So we want to develop some differentiable Lyapunov tools for this class of systems. And also the necessary and sufficient condition for synchronization of planar harmonic oscillators. We still don't have how to formulate it. And also extend our formation controllers to the case of general directed graph. And at the end, maybe I will do it here, if we'll be able to extend this problem, this framework for synchronization of a heterogeneous network admitting periodic orbit for the case of hybrid systems. Thank you for your attention. Time? Time is okay.
Can you go back?
Next one. Which one? For the first one. Yeah, it's inspired by the work of Mazank and Malizov. They have a book on construction of strict Lyapunov functions. And we use some of the ideas to build the Lyapunov function. I mean, it's a technical thing. We have to introduce some double integral of this matrix in our Lyapunov function. You take quadratic matrix, x transpose x, and you multiply this matrix by double integral of this term. And you have to choose the bounds of the integration. And when you derive, you end up with something strictly negative. Yeah, actually, for bidirectional graph case in Anderson, he proved that this condition of persistence of excitation of spanning tree is necessary and sufficient to have consensus uniformly. So what we mean by that is, since spanning tree is a minimal interconnection expected to have consensus, because we guarantee that the information flows in all the network, we have all the agent, and what we need here is just to be persistently exciting, which means the interconnection will not occur all time, but at certain intervals of time. So this one is necessary and sufficient for time varying. Yeah, the Laplacian. Yeah, actually, we can reformulate this condition in terms of Laplacian matrix. Yeah, we take the integral of the Laplacian matrix from t to t plus t fixed, and we show that this graph that we get is connected as constant graph, just as the time, but in time t. It's connected in each time t. You see what I mean? It's similar to what Moro gives here. So if you take this integral, you end up with graph. And if it is connected each time, then it's equivalent to our condition on resistance of excitation. For directed case, the conditions are more complicated because we need extra assumptions. Mm-hmm. Mm-hmm. If it is bidirectional graph, I think we approach the average of the initial conditions. Yeah? Yeah. I think so. Yeah, because if we multiply the Laplacian matrix but all one's element on the left, we will end up with the dynamic of the average which is equal to 0. So the average will be constant. And what will be affected by time is the errors. Exactly, yeah, in the last part. Mm-hmm.